Alright. This is almost the end of the year. We only have 13 units total. So we're getting pretty close to being done. Alright, this one is vibrations and waves. So this is going to be a lot about things moving back and forth over and over again, and sound. And depending on how this goes and how far along we get this week, we may combine this with the second, like one about light as well. Alright, so simple harmonic motion. This is just an object moving back and forth over and over again. And the mass and spring is just an easy way to think about it. If you stretch out the mass, let it go, it's going to bounce back and forth. Does that make sense? Eventually friction will slow it down in real life. We're going to kind of assume there's no friction in these. Okay. For the spring, the force exerted by the spring depends on the displacement of the spring. Does anybody remember what K is from energy, Brian?
It is a constant.
It's a constant. What a constant?
1.67 times 10 to the negative.
It's spring constant, different for every spring, but each spring has a specific one. Does that make sense? And X is how far it's been pulled from its equilibrium position. So its equilibrium position is where it would be if there's no force on it at all. Alright, and the minus sign indicates that the force is a restoring force. So that means it's like you pull it one direction and the force is applied as the opposite to that direction. So that's why there's a negative sign. Does that make sense to everybody? K is the spring constant, so I guess you probably could have just written it off of there when I asked. And the force is not constant, so the acceleration isn't constant either. So like as you let the spring go, what's going to happen to the force as it gets closer to its equilibrium position?
Can you repeat that?
Okay, so if I stretch out a spring, let it go, as it gets back closer to where it started, its equilibrium position, what happens to the force that the spring applies, do you think?
Higher.
Lower. So the less the spring is pulled apart, the less force it applies. So as the spring moves, the force decreases. Does that make sense to everybody? Alright. So simple harmonic motion. Displacement is measured from the equilibrium point. So our equilibrium point would be where x is equal to 0. So if we left the spring alone, that's where it would be at x equals 0. Amplitude is the maximum displacement. So it's the distance from the equilibrium point to where it gets the furthest away from the equilibrium point. Does that make sense to everybody? A cycle is a full to and fro motion. Each figure on here, like each step shows half a cycle. So like a cycle would be if we started here, we go there, back, and there. Does that make sense?
So
it doesn't just...
together is a part of the cycle.
What?
Pointed together.
Yeah, so it's not just getting back to the equilibrium position, it's getting back to the equilibrium position and going in the same direction. Does that make sense? So it's got to go, like let's say we pull it out here, it'd go there, and back to there. Does that make sense for one cycle? So I'd have to go, if we started there, we go there, and back. Does everybody kind of understand what a cycle is? We'll do it with the pendulum as well, which I think will be a little easier to understand. Alright, and the period is the time required to complete one cycle. So that's how long it takes to go back and forth. And the frequency is the number of cycles completed per second. So what do you think the relationship between the period and the frequency are? If one is seconds per cycle, the other is cycles per second. How can we get from one to the other? Inverse. So the period and the frequency are inverses of each other. Does that kind of make sense? So period equals 1 over frequency, frequency equals 1 over the period. Alright, and it kind of works the same way with energy. When the spring is as far compressed as it's going to be or stretched out, you have all potential energy. When it is back to its equilibrium position, all that potential energy has been converted to kinetic. Does that make sense? And then go out again, potential. When it's halfway in between, it's going to be some potential and some kinetic energy. And what's the equation for elastic potential energy? Anybody remember?
Oh yeah. P.
1/2.
1/2 K.
K.
Plus.
No.
K something squared.
K something squared. Anybody remember what something is?
The height.
Distance. So it's 1/2 K, or we usually call it delta x squared, so 1/2 kx squared. So 1/2 times the spring constant times the distance that's been stretched or compressed squared. And what's the equation for kinetic energy? 1/2 mv squared. 1/2 mass times velocity squared. Alright, so this is the equations for the period and the frequency of a mass and a spring. I'll put these on a worksheet when we do stuff with them later. So the period is equal to 2 pi times the square root of the mass of the spring times k. One thing I want you to notice about this is, does the actual distance the spring is stretched or compressed matter for how long it takes to go back and forth? No. So for a spring, it doesn't matter how much you stretch the spring out. It takes the same amount of time to get back to where it started. Does that kind of make sense? Can you think of why that is? Like, it's going a longer distance.
But if you pull it back more, there's more force pushing it
Yep. So if you pull it back more, there's more force, so it goes faster to get there. Does that kind of make sense? So the further you pull it back, the faster it goes. So no matter how far you've pulled it back, it takes the same amount of time to go back and forth. Anybody know what that would be useful for? Think about like something that goes in your wrist. A watch. So what they have in like mechanical watches or digital watches or something else entirely, but the watches that have like the ticking thing, a lot of those have a spring in there. It takes the same amount of time for the spring to go bouncing it out, and there's a little motor that keeps it bouncing, and that bouncing spring essentially keeps the clock, keeps the second hand ticking. Does that kind of make sense? And so because it doesn't take any longer no matter how far I stretch it out, even if it starts to lose power, it still clicks at the same rate even if it's not being pushed as far. And then frequency is just the reciprocal of that. It's usually easier to, I like the period equation better because 2 pi is on top, so I usually just find the period and then do 1 over the period to find the frequency if it asks for it. Okay. Pendulum works kind of the same way. I'm going to grab a pendulum. So I can hypnotize you during class.
Oh, Mr. Tent obviously does.
I know, Michael. Alright. So, pendulum. What would one period be in the pendulum?
Back.
Yep. So, take how long it takes to get back to here. Does that make sense? And if we were measuring it from like the equilibrium position, it would be like 1, 2, 3. So every time it passes this point going the same direction, that's 1 period. Alright, if you look at this equation, what matters for how long it takes to go back and forth? The length of the string. What else matters? Gravity. What is G? 9.8. In this case, we're going to use positive 9.8, otherwise we end up with taking the square root of a negative number, and that gets ugly. I mean, we technically should make the length negative, but that kind of doesn't make any sense, so we'll just keep everything positive. What doesn't matter that kind of you think might should? Weight. The mass of this doesn't matter at all. What else doesn't matter that could, some people might think should matter?
The length of
The height.
How far you pull it back. So it doesn't matter how far I pull this back, it takes the same amount of time to go back and forth each time.
Drop from height.
Once you start dropping it from up here, it gets different. But as long as this angle right here is small, it takes the same amount of time to go back and forth no matter how far you pull it back. So this was a Science Olympiad event one year. It's called, it's about time. And you had to make a clock out of a pendulum. It was actually surprisingly accurate. If you just set the pendulum, we set it so that it took a second for each period. So every time it got to here, you count 1, 2, 3, 4. And if you get the right length, it takes a second each time. You can actually predict, you'll lose maybe 1/10 of a second every 5 minutes or something like that. The hardest part was actually just keeping track of it and counting. And we're going to do that as a lab at some point, I hope, is we'll do a pendulum, and you guys have to make a clock out of it and see how accurately you can predict time. Does that make sense? Alright. And just so you know, this is one of those vocab words I usually don't talk about, but these equations are called small angle approximations because they work very well if that angle is small, but once you get out to like 45 degrees or more, they don't work quite as well.
What does that mean? The angles are small.
Like if you, so like,
roller coasters, like obviously that's not going to take the same amount of time. You know what I mean?
it does take approximately the same amount of time to go back and forth in those, but those are hydraulically, you have something called actuators on them. So those actually are mechanically slowed down back and forth. So not like free swinging like a pendulum. But when you say small angle, like Sarah, this is like a small angle, this would be a big angle.
Okay.
Does that make sense? It's like how far it is from being straight down. Yes.
Will our test be before spring break?
I'm planning on having your test be before spring break. This is a pretty short unit here. And I'm ruining your life, Michael. Alright, so wave motion. Okay, the reason why we talk about both these at the same time, let's say I have this pendulum swinging back and forth. If I graph like this motion over time with the graph underneath it, what would it look like?
Like that?
Like that. So, it would be a sine curve or a cosine curve. Alright, and just things on this. Amplitude is like the equilibrium position is if you drew a line and divided the wave in half. Amplitude, top is a crest, trough. You can measure the amplitude from either point. The wavelength is the distance between any two identical points in a wave. And by identical points, I mean it has to be doing the same thing, like either going up or down. So that's one wavelength from crest to crest. Trough to trough would be another. You can also go from like here to here would be another wavelength. But can you go from here to here? No. Why is that not a wavelength? It's going, in this case it's going down, in this case it's going up. It has to be doing the same thing at both points for it to be one wavelength. Does everybody understand that? Alright, what do you think would we call the frequency of this? How would we describe that of a wave like this that's going by? Jason?
The number of crests or troughs.
Yep. So to figure out the frequency, it's cycles per second. So it's really the number of identical points in a wave that go by every second. It's almost always measured with like crests though. So if we want to figure out the frequency of this wave, we time it and figure out how many crests pass by a certain point every second. Does that make sense to everybody? And then the period is just the reciprocal of that. And wave velocity is just how fast the wave moves. The important equation though is the velocity of the wave is equal to the wavelength times the frequency. And that kind of makes sense because if each wave is a meter and one wave passes by every second, that means it's moving at 1 meter per second. So you just multiply the frequency and the wavelength together. Any question on what any of those things mean? Okay. Two types of waves, transverse and longitudinal. Transverse waves are the actual thing the wave is moving through is perpendicular to the way the wave moves. So like if this slinky, if you flip it up like that, the slinky is moving up and down, but the wave is moving that way. Does that make sense to everybody? Another example would be like a wave in a crowd, so let's try that. Alright. Can you guys handle that? Alright, we'll start on 3 here. That was pretty weak. Alright, ready?
Yeah, turn the camera so they can all see.
Alright, turn the camera.
Follow it.
Okay. Ready? 1, 2, 3, go.
Gain some.
I would never surf on that.
Okay, people at CJ, sorry if my camera work on that was like nausea inducing or anything. Probably didn't go very well, but.
Who cares? Our basketball team.
Alright. Ellie. Alright. Alright, so we have the other type is called a longitudinal wave, and that's where the wave motion is parallel to the direction the medium moves. So in this case, if you took a slinky and squished it at one end, the wave would move this way, and the slinky would be moving back and forth this way as well. Does that kind of make sense to everybody?
Can you repeat that?
So like, if you take a slinky and squish it together like this, the slinky is going to get squished together like this. Does that kind of make sense? And the wave in the slinky is going to move that way. I'm trying to remember. I have here. 1 second.
Hi guys. Here we go, guys. Go Eagles.
I Michael?
I didn't know what to say. Why am I always the one in trouble? Yeah, I think
Alright guys, here's my giant slinky. Okay. Can I have a volunteer?
Oh! Oh!
Big Michael, come on in.
Let's make it with
Okay. So grab that end, kind of keep it spread out a little bit. Alright, so this would be a transverse wave.
You can't see it.
You gotta get it, yeah, get it a little higher.
There we
Right.
go.
So a transverse wave would be when it goes up like that. You guys see how like, yeah, do a little better here.
No, you're just too far.
Yeah.
you can see it.
No, you can see it.
The wave,
No, I can see
you see how the slinky moves up and down, but the wave in the slinky moves back and forth to me and Michael?
Yeah.
Alright, so for a longitudinal wave, we're gonna have to get a little like, not as slouchy. Alright, so a transverse wave is when it goes like,
Ooh.
actually I'd like to do this thing now. Alright, we're gonna bring it over here, we're gonna have somebody else do my camera work here. Just set it on the floor. Alright. Kira.
Got it.
Alright, set it on the floor and we're gonna watch the, you guys can stand up here. Alright, so a longitudinal wave is when I push it out like that. You see how the slinky moves like back and forth and the wave moves parallel direction.
That ain't
So I
even
push
real,
it that
bro.
way.
Whoa.
Just see how the slinky, like when the slinky actually moves, the slinky pieces are moving right and left, and the wave is moving right and left as well.
I got
So everybody understand that? Think you guys see how that works?
Here we go, Knights.
Stop.
Alright, so you can let it go for now, Mike. We'll do some more demonstration with this in a second.
That ain't
Put the
even real,
camera back.
bro.
I love slinky. Where can I get a slinky like that?
You can get it from a science catalog.
There's some water on the ground.
Alright. Okay, one important type of longitudinal wave, where it's like the compressions and things like that, is sound waves. So like when a drum goes in and out, if you bang on a drum, it goes in and then out, in and out, and it vibrates, and that's what makes the sound. So when it goes in, it creates something called a, they call it expansion here, it's also called a rarefaction. So that region of low pressure is a rarefaction. The region of high pressure when it's going out is called a compression. Speaker works in the same way, like your car or something like that. It'll go in and out and create high pressure areas and low pressure areas. And how you hear is when those high pressure areas and low pressure areas hit your eardrum, they cause your eardrum to vibrate at the same frequency they were at, and then the little bones in your ear detect that frequency and send the signal to your brain. Does that kind of make sense? So all sound is coming from vibrations of some kind that are creating compressions and rarefactions in the air. So high pressure and low pressure regions. Those high pressure and low pressure regions move through the air, and that's what you hear. So why is there no sound in space?
There's no air.
No air for it to go through.
No air.
John?
So how can you hear like more than one thing?
How can you hear more than one thing at once? What happens is those sound waves combine. It's kind of a way we'll talk about here shortly. So like when Brian's back there talking while I'm talking, you can hear him and me. I'm probably a little bit louder so you can hear me better because I create, like when a sound is louder, the high pressure is higher and the low pressure is lower than when it's softer. Does that make sense? So they'll combine, but the louder sound will create the higher and lower pressure and you hear that one better. Alright, energy transported by waves. A wave is able to spread out in 3 dimensions. So what actually happens is as you get further and further away from it, the intensity of the waves decreases by inverse square rule. So if you get twice as far away from like a sound source, the sound is 4 times as quiet. Does that make sense? And that's true for light too. If you get twice as far away from a light source, the light is 1/4 as bright because it's spreading out in all 3 dimensions. Does that make sense to everybody? Kyle?
Does that have something to do with like the sirens when they pass you?
That's the Doppler effect. We'll get to that in a second. Alright. Reflection and transmission of waves. So this is kind of, we'll get to this when we get to some of the instruments here later on. But alright, if you have a wave moving toward a fixed point, so if the wave is like pinned down, when it gets reflected back in the opposite direction. Does that kind of make sense? This is kind of hard to demonstrate, especially on the ground with the slinky. When it's loose at one end, it gets reflected back in the same direction. So if it's a fixed point at the one end, it's inverted. If it's loose at the other end, it stays upright. Does that make sense, everybody? Right. And so one more thing about reflection and transmission of wave, if you have like a light rope and a heavy rope, part of it gets transmitted, part of it gets reflected. This will kind of become important in the next chapter with light. But if it goes into a heavier medium, part of it gets transmitted, the part that gets reflected is inverted, the part that gets transmitted is upright. Does that just kind of make sense to everybody? Brian?
But if it was the other way around, would it just, from going from heavy to light, would it just like get bigger?
It's going from heavy to light, it would all be transmitted.
Would it get bigger or stay the same size?
It would get bigger. Alright, so this is one of the more important things we're going to talk about is when two waves meet. This is what Sean was talking about with the sound waves. So when two waves meet, if they are kind of opposites, they cancel each other out and then pass through each other and keep going. Does that make sense? If they are the same direction, they pass through each other and add together while they're at the same spot. So if you want to try a kind of interesting trick at home with speakers, you know how speakers have the red and the black wires?
Yes.
You got to put to make your speakers work right, you got to put the red one in the red one, the black one in the black one on the speakers. If you invert them on one of your speakers and push the speakers together, the sound waves will cancel out to an extent. Not perfectly, but they will. So like you take two speakers, put them together with the wires the correct way, it'll still be pretty loud. You flip the wires in one of them, and now when one's going out, the other's going in, so it's making the opposite. Like when one's making a compression, the other's making a rarefaction or a low pressure part. And the sound waves will cancel out, and because of the principle of superposition, they will eliminate each other as much as they can. It's not perfect, obviously, because it's...
You only hear like a very small amount.
You only hear a small amount of the sound, right?
Is that how the noise canceling headphones work?
That's how like the fancy noise canceling headphones work. They have to have a, I don't, most people, like, these are, I don't think these are the ones that like you can buy in the store. As far as I know, that like they have headphones like this, but I don't think they're commercial. But like they'll have a little speaker in them, and they'll create the exact opposite sound wave and play it into your ear. And it totally cancels out the sound. Does that make sense?
So
Yeah, I'm not sure if those are actually commercial. I think the ones that are commercial are just very heavily sound insulated, but
what if the ones that like do the opposite sound in your ear? What if that's like too much or something?
well, the microphone and the computer will decide how loud to actually make it as well. So it's not just like the opposite sound; it's the exact same volume as well. Okay. So these figures show the sum of two waves. So you see how these two waves are, we call it in phase. So all the peaks and troughs line up, and you get just bigger peaks and troughs. If they are totally out of phase, where one has a peak, the other has a trough, they cancel out completely. Most of the time, though, it's a combination of the two. You see how these two are just slightly shifted. So when they're slightly shifted, you end up with a slightly smaller wave when they combine. So if, like in this case, this would be like a slightly quieter sound, that would be no sound, that would be a much louder sound. Alright, standing waves and resonance. So maybe, like, here we'll do the slinky thing again. Oh, Michael just went to get a drink. Anybody else want to volunteer to play with the large slinky? Okay. Here, you want to do the camera work again here?
Yeah.
Grab one into that. Okay. So a standing wave is something that just keeps doing the same thing over and over again. So So you see how that keeps doing the same thing over and over again? Put your hand in it, right?
Do it.
It's a big metal slinky with sharp edges, so it probably kind of hurts.
It's sharp.
Not super sharp. Alright, so you see how there are kind of two bumps in this that keep going up and down? Those bumps are called antinodes. And that's where the displacement of the slinky is the greatest. You see that spot in the middle right there where it's barely moving at all? That's called the node. And there are, in this wave that I made right here, there are 2 antinodes where the big bumps are, and 3 nodes. So there's 1 node in the middle, and then where Kyle and I are holding it are the other 2 nodes. But
Can you make 3 into it?
like we can try going for 3. I think I'm gonna have to go faster or slower to get more.
Faster.
Slow.
If I go real slow, I end up with 1.
You can't even see this on the video.
Okay, it's like jump roping. Okay, now let's see how fast I can go here. There we go. That's 4. That's about the max I can get.
Okay, this is super hard to, you can't even see it on here. You really can't even see it.
Alright, we'll stop there. And just to let you know, guys, if you ever get anything like this, or happen to steal one from my room, is don't put it down the stairs, it won't work. It's too long. This thing has to be the right size for the stairs, so it'll just roll down the stairs and get all tangled up. Impossible to undo.
How far away does it have to be?
Right there. Should be good. Okay. Alright, so for waves and strings, so this would be like a guitar string or something like that. When you pluck it, it vibrates back and forth in those notes, and it, depending on how many there are and how fast the wave or guitar string is moving, that's what makes the note. So the guitar string, you pluck it, it vibrates up and down, and how fast it's vibrating is what note it plays. And the more bumps you have, the higher the harmonic. Hopefully that makes sense to some music people, but so the fundamental frequency, your first harmonic, is just 1 antinode. Second harmonic is 2 antinodes. Third harmonic is 3 antinodes. Does that kind of make sense for a string? Alright. So, just some things about sound. Sound can travel through any kind of matter, but not through a vacuum. It needs a medium to go through. What do you see happens as things get more dense? Does the speed of sound increase or decrease? As the density increases, the speed of sound increases as well, in general. So you see in iron it's about 5,000 meters per second. In air it's only about 330. And the general equation for the speed of sound in air is 331 plus 0.6 times the temperature in Celsius. So if you end up with a negative temperature, you subtract from that. So the speed of sound in water is greater than it is in air. Why don't you hear as much in water as you do in air, do you think?
The sound disperses.
It takes more energy for the sound to travel through water than air. So the particles in water are more concentrated and heavier. So for them to vibrate, it takes more energy out of that sound wave. So it has to, in water, it has to get through more molecules to get to your ear than it does in air. Does that make sense?
So it's moving fast.
It's moving.
Still moving fast.
It's moving faster, but every foot it goes through, it loses more energy than it does in air because it's got that foot of air versus that foot of water. There are more things to move in the water than there are in the air. Does that make sense? Alright, so a couple more characteristics of sound. Loudness is related to the intensity of the sound. So that's how big the wave is essentially, or how in sound it's how high pressure the high pressure regions are and how low pressure the low pressure regions are. Pitch is the frequency, and the frequency that you hear is how many high pressure regions hit your ear every second is what the frequency is. So the more high pressure regions that are hitting your ear every second, the higher the pitch of the sound is. The audible range people can hear is about 20 hertz to 20,000 hertz, and that upper limit decreases with age. How many of you guys have seen the little cell phone rings that teachers are not supposed to be able to hear?
The high pitch.
The high pitched. Yep.
That's not funny.
He laughs at everything because he's a good person.
That's me.
The cell phone rings, as you get older, you can't hear as high pitches anymore. So they take advantage of that, and most teachers, like, I used to be able to hear them when I was like 22 and just started teaching. I don't think I can hear them anymore.
Don't speak.
Is there a difference between boys and girls?
But and there's a general difference between like
That one was, yeah, someone's Delta Boys or something. My brother has on his iPod, and he'll play it, and he can't hear a thing, but I can somehow. It bugs the crap out of me. Is there a big difference?
there's more of a difference. I think it's just between individual people as opposed to sexes. I'm not sure on that though. I have to admit, that sounds like a good science fair project. All right. So we call ultrasound is sound that is above 20,000 hertz, so nobody can hear it. And infrasound is below 20 hertz. In general, other animals usually can hear higher pitches than we can. So, like, you guys know what a dog whistle is? It's a dog whistle only a dog can hear because we can't hear that high pitch the way the dog can. Like, it's still vibrating in our eardrums, but it doesn't register for like our brain essentially. All right, frequencies and strings and pipes. These are just some equations. I'm gonna go through what they mean. In a string, the frequency is equal to n, which is the harmonic. That's usually going to be 1, times the speed of the wave in the string, times 2 times the length, or divided by 2 times the length of the string. In a pipe, open at both ends. So this would be like a flute. There's a pipe open at both ends. The frequency is equal to n, which again is usually 1. The v in this case is the speed of sound in air, divided by 2 times the length of the pipe. So how like for example, if you're playing a flute, what you do when you cover the holes, you're changing the length of the pipe. Does that make sense to everybody? And then in a pipe closed at one end, the frequency is equal to n times v over 4 times the length. So a pipe closed at both ends would be like a reed instrument, like a clarinet, because you effectively close the other end with your mouth. Does that kind of make sense? And again, you change the length of the pipe by pushing the different keys down. Alright. Almost done here, guys. Doppler effect. This is what Kyle was talking about before when a car comes toward you. So the you guys all know that sound, like at a racetrack or something like that. Michael?
Have you seen The Big Bang Theory? Do you watch that at all?
I've seen where he dresses up as a Doppler effect.
Yeah.
Is that an accurate?
I think it is an accurate. I haven't actually seen that one, but I think that is an accurate representation. So what actually happens with the Doppler effect is, like in this picture, the fire engine standing still. The sound waves spread out in all directions, and both people hear it at the same pitch. Does that make sense? If it's moving this way, now every time it emits another sound wave, they're further apart than they should be for the guy behind it. So if they're further apart than they should be, he hears a lower frequency because they're hitting him less often. So the frequency on this side is lower, so that's why after the car goes by, it's so when something's gone by you, the frequency gets lower. When it's moving toward you, now they all stack up, and the frequency you hear is higher because you're getting more of like each compression per second. Does that kind of make sense to everybody? Alright, this is the equation for the Doppler effect. F is the frequency you hear. FO is the frequency you'd hear if everything was standing still. And then the V's are the speed of the observer and the source. And we'll do some math with that later on here. I think this is the last slide. Never mind. Well, 2 more slides and we're done. Alright, shock waves and sonic booms. How many of you guys have seen, like in a boat, where are the biggest waves when you're driving?
Behind you. On the sides of the boat?
They line up, coming off like in a triangle from the boat. Those are called bow waves, and they form a shock wave. So what happens then, here's your boat in still water. Pretend it's spreading out waves in all directions. Once it starts to move, the waves in front of it get closer together, and they get closer together on the sides here too. Once it moves with the same speed as the speed of the waves in the water, now all the waves start to line up along the same spot. Does that kind of make sense? And once it's going faster, now they all line up along here, and that's where you see the bow wave in a boat. And it's also why you get a sonic boom in an airplane. Once the airplane moves as fast as the speed of sound in air, all the sound waves line up. So it's moving faster than the speed of sound in air. Say you're standing like right here when the plane flies by. You actually see the plane fly by first. And then once this wave catches up to you, you'll hear like a sonic boom after it. Does that kind of make sense? Enough?
Sure. Why do they form a cloud around it when they break the sound barrier?
Because this high pressure area right here all lines up, and it's kind of like, have you ever like opened like a soda bottle and like the steam comes out? So that's pressurized, and when you let the pressure out, it all evaporates almost at once. So what happens here is that high pressure area hits and compresses all the air, and then it decompresses, and it like kind of will form like a water drop necessarily, but a heavy water vapor. And then when it decompresses, it all evaporates immediately. Alright. And last thing is beats. This is if you have two different frequencies and what they do. So let's say we have a 50 hertz sound, which is the frequency of 50, and a 60 hertz sound. You see how they don't quite line up all the way? What happens is they add together and you hear like a pulsing sound. So where they add together totally, you get a really high, and when they completely cancel out, you get really low sound, and you hear this. So they add together in beats, and I think the equation for that is something we'll do on the worksheet at some point here. Does that kind of make sense how they add together and you'll get like a pattern forming, and it becomes like a new frequency of sound? Alright, any questions on any of that?
Have a good day.